So, as our friendly one-eared rabbit suggests, today's the day we talk about applying Gauss's law. I hope you're as excited about this prospect as is Bongo. As you and Bongo will come to appreciate, I'm sure, Gauss's law will allow you to very easily determine the form of the electric field surrounding a charge distribution, so long as the charge distribution possesses sufficient symmetry, okay, as we'll see. Let's start, however, by quickly reviewing what Gauss's law tells us about electric fields. So in words, okay, Gauss's law tells us that the number of field lines, and we're talking about electric field here, so the number of electric field lines penetrating a closed surface is proportional to the charge enclosed by that surface. The number of electric field lines penetrating the closed surface, that's what we call the electric flux through the surface. And the electric flux, by definition, is described in terms of the surface integral, okay, which is the dot product of the electric field with that infinitesimal area vector dA. And once again, we put the S to represent a surface integral, as opposed to a line integral. You can tell here that dA tells you that it's a surface we're looking at as opposed to a one-dimensional line segment, as in the case of a line integral, okay, a one-dimensional displacement vector. And of course, the closed circle tells you that we're looking at a closed surface only. And of course, on the right-hand side, to say that the number of electric field lines penetrating the closed surface is directly proportional to the charge enclosed by the surface, we turn that proportion into an equation by introducing this proportionality constant, 1 over epsilon naught. All right, so a few notes about the meaning here, as we'll see, very important, okay, that you know when you can apply Gauss's law, okay, and what it applies to. First of all, as we said, it applies to closed surfaces only. Okay, so your surface, okay, doesn't tell you exactly what type of surface, but it does have to be a closed surface. Okay, no holes, okay, in that surface. And this is probably the most important point here, that the electric field that is contained in this surface integral, okay, represents the total electric field due to charges that are both inside and outside of that closed Gaussian surface. So I just want to make clear that the electric flux, okay, is going to be affected by charges that are everywhere in space, regardless of how you draw your surface. So don't think that, just because we're looking at the charge enclosed by the surface, that it only tells us the field in that region. And finally, I'll say this, and while Gauss's law is always true, okay, it would apply for any charge distribution in the same way that Coulomb's law does, okay? In previous week, we talked about how to evaluate electric fields, okay, by using Coulomb's law. While it is always true, it is not always useful. As we will see, it is only going to be useful. You are only going to be able to evaluate that surface integral, okay, when you have sufficient symmetry to your charge distribution. And this will become very clear in our discussion today. What I'm going to say in this slide may seem a little bit abstract, a little bit theoretical, but I will say that after we actually get some practice applying Gauss's law, when you come back and you look at this slide, it will make a lot more sense. Okay, so you may need to do that. But let's talk about the reason for introducing Gauss's law. Think about what we did previously. We were able to calculate the form of the electric field surrounding a charge distribution by basically using Coulomb's law. And we were able to do this. Okay, our approach was to take that charge distribution, divide it up into an infinite number of infinitesimally small charge elements dq, okay, where we would figure out the contribution that each of those small charge elements made to the electric field at the field point in question. And by then summing up all of those, okay, infinitesimal contributions to the field due to each dq, which amounted to, in the language of calculus, taking the integral, we could then figure out what the total field looked like at the field point in question. But while we were able to solve many problems successfully, in other words, find out what the electric field looked like for many different charge distributions, it wasn't always easy. And as Bongo suggests here, that unit vector r hat, for many of our problems, it proved problematic when we had to apply Coulomb's law, okay, because the direction of r hat changed with each dq. Now, I'll be honest, for the finite rod that was along the x-axis, the very first problem we solved using Coulomb's law, when the field point was also along the x-axis, for that case, the direction of r hat didn't change. That was kind of unique, okay? And like I said, we were able to actually use Coulomb's law, and with some, this concept of charge density, some trigonometry, okay, using some symmetry, we were able to figure out what the field looked like. But as we will see, Gauss's law is much more elegant, okay? It is actually much easier to use to find out what the form of the electric field looks like for certain charge distributions. So the key is, when can we use Gauss's law? Well, Gauss's law is only useful, we only want to apply it for highly symmetric charge distributions, okay, where the direction of the electric field can be easily predicted at all points in space. It can be predicted because of the high degree of symmetry. And if you're saying, well, this still seems so abstract, we're going to make it really concrete. It turns out there really are only three types of charge distributions that possess sufficient symmetry, okay, to where Gauss's law is useful. So let's state what these are. The first is a charge distribution with spherical symmetry. Okay, when that applies, use Gauss's law. The second case is for a charge distribution with cylindrical symmetry. So we're talking about a right circular cylinder. Okay, and the third and final case is for a charge distribution with planar symmetry. Okay, so this is pretty specific. There's really only three types of charge distributions for which sufficient symmetry exists to where Gauss's law is actually useful, where we can apply it. Now, the second thing I'll say is that, when the flux surface integral can be evaluated without knowing exactly what that electric field looks like, and let me be more specific. Let's say when that electric field is at least piecewise constant over the chosen surface so that it can be taken outside of the integral. If this condition is not met, okay, it would be a nightmare to actually apply Gauss's law and evaluate that flux integral. Okay, but as we will see, for these symmetries that we're going to talk about, with the appropriate choice of the Gaussian surface, the electric field, okay, will be at least piecewise constant over every piece of the surface, in which case it makes evaluating that integral possible. In the next two slides, we're going to outline a step-by-step procedure for how to go about applying Gauss's law. Now, I'll admit this is going to make a lot more sense once we actually apply these steps, okay, to some particular charge distributions, okay, which we're going to do, okay, but let's at least first state these steps, okay, and I promise they will make a lot more sense when we get to the examples. So bear with me for a second here. The first step, identify the symmetry of the charge distribution. Like we said, Gauss's law is only going to be useful. We're only going to use it for these three highly symmetric charge distributions, right? Spherical symmetry, cylindrical symmetry, or planar symmetry. Once you've identified that symmetry, you're going to choose a Gaussian surface, okay, to match the symmetry of the charge distribution, okay, such that for all parts of the surface, okay, these two criteria are met. And again, this may not make a lot of sense now, but it will when we start to solve the problems. The first criteria when you're choosing your Gaussian surface is that, okay, the magnitude of the electric field must be constant. Okay, it may be zero, but it must be at least constant, okay, for each piece of the surface, if not for the entire surface as a whole. Okay, or if the electric field is not constant over that, the magnitude of the electric field is not constant over that piece of the surface, then the electric field must be perpendicular to this area vector dA, in which case the flux due to the field for that portion of the surface will be zero. Okay, if the electric field was not constant in magnitude, it becomes impossible to evaluate the flux integral unless, okay, this condition is met. Okay, if the electric field is perpendicular to that area vector dA, then there is no flux through that piece of the surface, in which case the flux is zero. So, as we said, okay, there's only three types of symmetry, and you will see this is pretty simple. Each special type of symmetry gives rise to a unique Gaussian surface that reflects that symmetry. And this is not going to be too hard here. If you have a charge distribution with spherical symmetry, okay, then your Gaussian surface is going to be a sphere. Okay, if you have a charge distribution which has cylindrical symmetry, in other words, the charge distribution looks like a right circular cylinder, guess what? Your Gaussian surface, okay, is also going to be a right circular cylinder, oriented in a certain way, as we'll see. The planar distribution, charge distribution, this may not seem so obvious now, it will when we solve the problems, but you'll write it down anyways. Okay, for a planar symmetry, then your Gaussian surface is going to be what we call a Gaussian pillbox. It is a right circular cylinder, okay, I mean it could actually have some other shapes, but it will have a special orientation, as we'll see. So, this is pretty formulaic. Given a problem, you're going to have one of these three types of symmetry. It's going to be obvious, and therefore the Gaussian surface you choose should be obvious. So steps 1 and steps 2, okay, steps 1 through 2, very straightforward. Step 3, you really want to try to draw a picture of this, in part to help you see what's going on, and in part to be able to explain to me, okay, what you're doing so I can give you credit. So once you've identified the charge distribution and the Gaussian surface, you're going to draw the appropriate Gaussian surface along with the charge distribution, of course, so that the surface passes through the point where the electric field needs to be evaluated. So somehow, wherever it asks you to find the electric field in the problem, you know, call that point P, your Gaussian surface must end on that point. And we are then you're going to use the symmetry of the charge distribution to determine the direction of the electric field on each part of the surface. So we said Gauss's law is only useful when you can do this, when the direction of the electric field is obvious. It's obvious, okay, because of the high degree of symmetry. If you could not predict the direction of the electric field, then Gauss's law, while true, is completely unuseful. So where are we at? Well, we've identified the symmetry of the charge distribution. We've drawn it on our piece of paper, okay, and that symmetry dictates exactly what type of Gaussian surface we're going to use to match that symmetry. So we've drawn the Gaussian surface on the piece of paper so that it passes through the field point, okay, the point where we're asked to find the field. And then we've drawn the direction of the electric field, okay, for each portion of the surface. I want to say that for a sphere has only, one side, one portion of the surface. But for a right circular cylinder, it really has three pieces. It's got the sides of the cylinder and then let's say the two ends. Sometimes we call these end caps. So you want to draw in what is the direction of the electric field for each of those three pieces. It is also a really good idea to draw in, okay, this infinitesimal area vector dA as well, because that's going to help you when it comes to evaluating the flux. And once you've got this, you are now ready to evaluate the electric flux, okay, for either the surface, or let's say each piece of the surface individually. Here's what's going to happen, okay, believe it or not, okay, one of these two things is going to happen. With the appropriate Gaussian surface, either, okay, this integrand E dot dA, okay, it will be 0. Why? Okay, because the electric field is going to be perpendicular to this infinitesimal area vector dA, which means that if it's perpendicular to it, then it means none of the field lines penetrate that piece of the surface and there's no flux through it. So this is one possibility. Believe it or not, the only other possibility, the only other thing that can happen would be that the electric field is either parallel or anti-parallel to that area vector dA. In which case, if it is in the same direction as dA, okay, then this dot product, E dot dA, is simply equal to the magnitude of E times the magnitude of dA, which is just the area of that piece of the surface, times the cosine of 0, which is just 1. If it's anti-parallel, if they're in opposite directions, then it's going to be minus E dA, right? Because you're going to be taking the cosine of 180 degrees rather than the cosine of 0. And the magnitude of that electric field for that portion of the surface must be constant. Those are the only possibilities. And because of that, okay, either the flux is 0, in which case evaluating that interval is easy, or the second possibility, if the flux is equal to plus or minus EdA with the magnitude of E being constant, you'll be able to take the electric field outside of the integral sign. Okay, and once you've done that, okay, you can do this for each piece of the surface. Okay, you've evaluated the electric flux. Okay, for each piece, you know the total electric flux or the net electric flux. You now can calculate the charge enclosed by the Gaussian surface. Okay, and I just want to point out here that, very often the charge enclosed, it may be a point charge, in which case, there's nothing to this. It's obvious. There may be no charge enclosed by your Gaussian surface. Okay, but what is often very common is that there will be charge enclosed by your Gaussian surface, and the charge enclosed you're going to have to figure out. So you're going to have to use this concept of charge density, in which case for a three-dimensional charge distribution, you're going to say the charge enclosed is equal to, okay, rho, the three-dimensional charge density, times the volume of the charge enclosed by the surface. So only the charge enclosed that counts. For the case of a two-dimensional charge distribution, it's going to be equal to the surface. Okay, the charge enclosed will be equal to the surface charge density times, okay, the area of the charge enclosed by that Gaussian surface. Or for the case of a one-dimensional charge distribution or linear charge density, then you will take, okay, the linear charge density times the length of the charge enclosed, okay, by that Gaussian surface. I want to point out again, only the enclosed charge matters. If there's charge outside of the Gaussian surface, ignore that. It doesn't come into play. Now that you've, in step 5, figured out the left-hand side of Gauss's law, and in step 6, you've almost figured out the right-hand side of Gauss's law, now you just need to equate these two expressions, and don't forget that proportionality constant, epsilon naught. Okay, and as you will see, you're going to be in a position to solve for the magnitude of the electric field. Remember, the direction of the field is already known. okay, but the magnitude of the field you will get by, okay, applying Gauss's law here, equating the flux with the charge enclosed. And I'll say here, note that, okay, the electric field represents the total electric field due to charges both inside and outside of the Gaussian surface. Not the first time I've said this, okay, but remember that you are finding the electric field everywhere, okay? So when you draw your Gaussian surface, some of the charge will be enclosed by the surface, some will not, okay, but the field you find will be due to all charges everywhere. Now that we've outlined these steps for applying Gauss's law, okay, to these special highly symmetric charge distributions, okay, let's actually not just talk about how to do this in theory, let's do it. So let's look at some specific examples of these highly symmetric charge distributions and see how Gauss's law can very elegantly figure out what the electric field looks like, okay, at various points surrounding them. The first example we'll look at is the case of the uniformly charged solid spherical insulator. I say insulator because remember that for an insulator, charges do not move easily. So if there's charges that exist at a certain point in that insulator, those charges, okay, will stay there. They won't move. The case of conductors, remember the charges can move easily. And we will talk about the case of conductors next time. So in this problem, we're told that a uniformly charged sphere, okay, of radius A with a total charge plus Q, it's a positively charged sphere, and it is uniformly charged. So it is a solid sphere having this uniform charge distribution with a total charge plus Q. The first part of the problem asks us to find what the electric field looks like, okay, for points for which R is greater than A. These are points outside of the charge distribution, okay, where the distance from the center of the charge distribution to these points is greater than, okay, the radius of the charge distribution itself. So basically for points outside. So step one, identify the symmetry of the charge distribution. Well, that's obvious, okay, it's spherical. Step two, choose the Gaussian surface to match the symmetry of the charge distribution, okay, such that all parts of the surface, okay, for all parts of the surface, the electric field magnitude is either constant, okay, and or if it's not constant, then it will be, the electric field will be perpendicular in direction to dA so that none of the field penetrates the surface, in which case there's no flux for that part of the surface. And as we said, you don't really need to think about this because I've already pretty much told you what these surfaces are. For a spherically symmetric charge distribution, okay, you're going to choose a Gaussian sphere. And we will make this sphere of radius r so that it must go through the field point in question. So we're going to now draw the Gaussian surface so it passes through the point where the electric field needs to be evaluated. We're evaluating the field outside of the charged sphere. I will choose a random arbitrary point here. Okay, I could have drawn that anywhere. And we will say that that point is okay, a distance r from the center of our charge distribution. Okay, see how easy this is, folks? We're now going to use the symmetry of the charge distribution to determine the direction of the electric field in each part of the surface. For a sphere, okay, and this is where, you know, hopefully this concept of symmetry makes sense to you. Spherical symmetry suggests that there can be no angular dependence to the field. The field can get weaker with distance, okay? It can depend upon, okay, the radius or the distance you are from the center of the charge distribution. But the symmetry would tell us that, okay, as long as you are the same distance away, okay, then the magnitude of that field should be the same, and the direction of the field, okay, must be in the radial direction. Okay, it must be directed radially outward. Okay, in this case, because our charge distribution is positive, it's a positive charge, and so how we define the electric field, remember to be the direction that the force would, on a small positive test charge, okay, what would be the direction of the force on that small positive test charge when you put it at the point where you're evaluating the field. So in this case, it has to be in the radial direction. There can be no angular dependence to it. So here we go. I'm drawing several electric field vectors, okay, and you'll notice that there is no angular dependence to the field. Okay, it is in the radial direction only. It points outwards because our charge distribution is positive. And so you can see the direction of the electric field on every part of that surface. Notice that, okay, when we evaluate the electric flux, let's draw in what that infinitesimal area vector dA looks like. So let me draw in one of those examples here. And you'll notice here that, remember, that very small, that tiny little area has to be parallel to the area is a little piece of that surface, and the vector is perpendicular to that piece of the surface. Notice that in this case, and by the way, dA is always an outward pointing normal. Doesn't matter what the charge is. Okay, dA is always an outward pointing normal by convention. So you'll notice here that the direction of the electric field and the direction of dA is the same everywhere. So when it comes to evaluating the flux here, it makes this particularly easy. The electric field will be constant in magnitude, okay, over every part of that surface because, okay, of the symmetry involved. Because the magnitude of the field depends upon, okay, how far you are away from the center of your charge distribution. And for a sphere, you are the same distance away, okay, on that entire surface. So here, when we look at our flux integral, we already said that the angle between the electric field and the dA vector is 0. So we're taking the cosine of 0 when we evaluate the dot product. Okay, and as we said previously, up here, you get a laser pointer here, that E has to be constant. With this choice of surface, the magnitude of the field will be constant, okay, over every piece of the surface. Okay, and if it's not constant, the flux will be 0. The flux is certainly not 0 through the surface, but you will notice that the field is constant at every point. Looking at my laser pointer, what I'm saying is that the magnitude of the electric field at this point will be exactly the same as the magnitude at this point, the same as the magnitude at this point, because, okay, each of those points is the same distance away from the charge distribution. So, given that, okay, this tells us that we can take the if E is constant over that surface, it can be taken outside of the integral. Like I said, this will always be the case with these chosen surfaces for these symmetries. In which case, it will always be the case that if your flux isn't 0, all you're going to end up doing is evaluating the surface integral, okay, for that area vector dA. What does dA represent? It is simply that infinitesimal area for that small piece of the surface. What do you get when you add up all those infinitesimal pieces of area for the entire closed surface? You just get the total area of the surface. Okay, this is easy, right? So for our Gaussian surface, the surface area is just 4 pi r squared, okay, the area of that sphere. So you see that evaluating the flux is really not hard, okay? If it's not 0, okay, then the electric field will be constant, can be taken outside of the integral, and your integral is simply going to be, okay, the area of that Gaussian surface. So we're done with step 5. Okay, step 6, calculate the charge enclosed by the Gaussian surface. Well, in this case here, the surface encloses the entire charge distribution, which has a total charge plus Q. Okay, it's obvious, so this is easy. Last step, all we're going to do is equate these expressions and incorporate that proportionality constant epsilon naught. So let's go ahead and take, okay, our flux here, E times 4 pi r squared, set it equal to the charge enclosed, which we just said was plus Q, divided by epsilon naught. And we now solve for E, and we're done. right? E is 1 over 4 pi epsilon naught. Remember, 1 over 4 pi epsilon naught is simply Coulomb's constant. Okay, so we end up getting K times Q over R squared. And what this is really telling us is that the electric field outside that charge distribution is exactly identical or equivalent to the case of a point charge. If all of that charge, that spherical charge, was located at a single point at the center, okay, then it would give us exactly the same electric field there. All right, in the second part of this problem, we're still considering the same charge distribution, okay, but now we're asked to find what does the electric field look like at points inside of the charge distribution, for which the distance is actually less than the radius. So, as you'll find in this slide, pretty much everything we did to set up the problem in the last slide applies equally well here. So we'll go through this very quickly. Our charge distribution is still spherical in symmetry. The Gaussian surface, therefore, which satisfies this criteria, okay, such that the magnitude of the electric field is constant, or at least piecewise constant over every part of the surface, and/or, okay, the electric field is perpendicular to, okay, that area vector dA, which means that there's no flux through that part of the surface. Okay, these conditions are automatically met when we choose a spherical Gaussian surface. Okay, so when we draw that Gaussian surface, the only difference is that we always draw the Gaussian surface going through the field point. Well, now we're looking at a point inside of the charge distribution. So let me pick an arbitrary point here. We will draw our sphere so that it goes through that point. Okay, and we will say that that Gaussian surface, really a Gaussian sphere, has a radius r, okay, which is variable. We're going to use the symmetry of the charge distribution to determine the direction of each part of the surface. Now, we're going to talk a little more about this at the end of the next slide, but okay, for now, we know that for positive charges, okay, then the electric field is always directed away from positive charges. This is a spherical charge distribution, spherical symmetry, so we know that, okay, the electric field will be directed radially outwards rather than inwards. And like I said, we'll talk a little more about that, okay, at the end of the next slide. So the only part that looks different here is really where we draw our Gaussian surface, because the field point is inside of the charge distribution versus outside. Okay, when it comes to evaluating the flux here, okay, nothing new here either. Right? Notice that at all points on that Gaussian surface, okay, this infinitesimal area vector dA, this outward pointing normal, is in the same direction as the electric field. Notice, once again, the electric field is constant in magnitude over every part of that surface because it's the same distance from the center. The field has the same magnitude, in which case it can be taken out of the integral sign. Field and dA being in the same direction gives us cosine 0. Field being constant in magnitude means it can be taken out of the integral sign. So once again, this will always be the case with Gauss's law. When you evaluate that surface integral, all you're going to be really doing is summing up all of those infinitesimal pieces of the surface, little surface area elements, so you get the total area of the surface, okay, which is exactly what we got in the previous slide in part 1 of the problem. Okay, a sphere has a surface area of 4 pi r squared. So nothing new here other than our picture. Okay, what we'll look at when we finish the problem in the next slide, there will be, okay, a little bit, there will be something new. So, okay, we'll get there in a sec. So now we know what the expression for the electric flux looks like. Okay, that is the left-hand side of Gauss's law. And we said it is really identical to what we determined in part 1 of this problem. Okay, but we're now in a position to calculate the charge enclosed by the Gaussian surface. Okay, and this is the part that's a little bit different. For the first problem, we were looking at what the field looked like outside of the charged sphere. Okay, then our Gaussian surface enclosed all of the charge. Okay, but for part two of this problem, our Gaussian surface encloses only a part of the charge. But because the charge distribution is uniform, we can use the concept of charge density and say, okay, the charge enclosed would just be equal to the charge density, okay, times the volume of our Gaussian surface. So let's start the problem. We need to, in this problem, calculate the charge density. It's not given to us. Remember, for a uniform charge density, the charge density is simply the total charge per total volume, total area, or total length, depending upon the dimensionality of the charge distribution. This is a three-dimensional charge distribution. Okay, so we're looking at a three-dimensional charge density, which is simply the total charge of our sphere divided by the total volume of our sphere, which has a radius a, which would be given by 4/3 pi a cubed. There we have it, charge per volume. That is for the entire charge distribution or any piece of it. Any piece you want to look at, the charge density would be the same because it is uniform. It is constant throughout. So given that, we can now figure out just how much charge is enclosed by the surface, by the Gaussian surface. The charge enclosed is just equal to this charge density times the volume of the Gaussian surface. So we take this here. All right, our expression for charge density, we're going to multiply by the volume of our Gaussian surface, which is just 4/3 pi r cubed. And when we simplify and we cancel any common factors here, we get, okay, Q, the total charge, times this ratio r cubed divided by a cubed. Okay, last step in the problem is simply to equate the left-hand side of Gauss's law, the electric flux, with the right-hand side, which is simply the enclosed charge divided by this proportionality constant epsilon naught, and then solve for the magnitude of the electric field, okay, since we already know its direction. So doing that here, all right, we can get rid of this common factor of r squared on both sides, divided by 4 pi. We end up with this. So this is the expression for the field, okay, how the magnitude of the field inside of the charge distribution. Notice here that when you're outside of the charge distribution, the electric field, okay, gets smaller as the square of distance. When you're inside the charge distribution, okay, the electric field gets bigger linearly, okay, with r. Okay, with the distance you are from the center of that charge distribution. So we can try to graph this, and hopefully you see why this becomes the shape of our graph. Okay, what we're saying is if we're looking at a graph of the electric field versus radius, okay, which really means distance from the center of the charge distribution, right at the center, okay, the electric field would be 0 because there would be no charge beneath it, no charge enclosed. But it looks like as you get further away from the center, the electric field increases linearly up until you get to the edge of the charge distribution at a radius a, up to this point. So the field increases linearly up to this point, and then we see what happens, okay? It obeys this inverse square law. It drops, okay, as the square of distance, which is what we found in part 1. Remember that when you're outside of this, what we said is that basically this charge distribution behaves as a point charge. It is as if all of the charge of this entire sphere was located at a single point at its center. You get the same field outside a spherically symmetric charge distribution as you would, okay, for a point charge. So that's a very important conclusion. And remember that in solving problems, okay? It can often make problem solving very simple. All right, so there we have that. I want to go back to a point that I said we would come back to, and that is why does the electric field, okay, point outwards at the Gaussian surface here in this part, when we look at charge outside the surface, okay, shouldn't that direct the field inwards? So for example, at this point P here, if I'm looking at charge outside of my Gaussian surface, shouldn't that exert an inward force here? At this point, shouldn't the field contribution be inwards rather than outwards? Okay, and so the real question is, why did we automatically draw the electric field to be outwards? Well, this may harken back to our discussion of gravity. When we looked at a spherically symmetric mass distribution, we said really it's only the mass, okay, underneath, okay, the field point that counts. So for example, if you were in a uniform Earth and you were deep in a cave, what we're saying is that only the mass between you and the center of the Earth that is underneath you would contribute to the gravitational pull on you. Any mass that was between you and the surface of the Earth would not, for exactly the same reason I'm going to show you now. Okay, so let's take a look at that. If I look at putting a test charge here, okay, and if this is our Gaussian surface, and I want to look at the direction of the field on that test charge, okay, well, I would say that some of this green charge, which is positive out here, should direct the electric field at that point in this direction. Okay, but here's inwards, which is not what we drew in the picture. But here's the thing, okay, for every bit of charge that is on this side of the field point, where I put my little test charge here, okay, there is going to be an element of charge on the opposite side of the sphere, okay, that is going to make a contribution to the field. That would be, again, field always points away from a positive charge. Okay, so this green sample of charge here would exert a force in a field on this test charge in this direction. And I'm not showing you it here, but using calculus, you can show that those two forces and therefore field contributions are exactly identical. The end result is that it's only the charge that is, okay, really underneath you between the center and that field point that is going to make a contribution. Okay, any charge outside of the Gaussian surface here is going to cancel. And so what we find out for, okay, electric charge is exactly what we found out for the case of gravity. All right, so this next problem asks us to find the electric field at distance r from a long straight wire with uniform positive charge density lambda. It says assume that the electric field is calculated far from the ends of the wire. So we can't draw an infinitely long wire, but okay, we will assume that it's very long and where we're trying to find the field is nowhere near the ends of the wire. So as I said, let's start by trying to draw the charge distribution. And you'll notice that a wire is really a right circular cylinder. Okay, if the wire is very thin, this may not be obvious, but if the wire was thick enough to maybe call a rod, then you would see that it's a right circular cylinder. And if the charge is uniformly distributed, okay, through that conducting wire, then we would assume that it has cylindrical symmetry. So identify the symmetry of the charge distribution. It's cylindrical. It's a right circular cylinder. We're going to choose a Gaussian surface to match the symmetry of the charge distribution for all such that, okay, the electric field is either constant on all parts of the surface, and or if the electric field is not constant, it contributes no flux. Okay, the electric field doesn't actually penetrate that part of the surface. And as we said, Anytime you have a charge distribution that you consider to be a right circular cylinder with cylindrical symmetry, then the Gaussian surface you're going to choose is, guess what, a right circular cylinder. And just tell yourself that you're going to see why this condition here, these conditions will be met with this choice of Gaussian surface. We're going to say that just like for the sphere, we said the radius of the sphere was r. Okay, here we'll say that the radius of our cylinder is r, and we'll say it has a length L. We're going to draw the appropriate Gaussian surface so that it passes through the point where the electric field needs to be evaluated. Now here, we're asked to find the field outside of the charge distribution. Let's say at this arbitrary point P here. So we will draw our Gaussian surface like this. Okay, it has a radius r, and okay, it has a length L. So from here, we're going to use the symmetry of the charge distribution to determine the direction of the electric field on each part of the surface. As I said previously, a right circular cylinder has two ends in the sides. Okay, it's really one surface part, and so we're going to have to look at each part of that surface separately. So I'm drawing what the electric field would look like. This is a positive charge distribution. And again, because of the symmetry, because of the cylindrical symmetry, we see that the electric field is going to be directed radially outwards. Okay, there can be a radial dependence, but there can be no angular dependence, okay, because of the symmetry. That this rod looks the same, okay, through any, angle theta or phi, okay, when you're looking at, let's say, cylindrical polar coordinates here. The only, field dependence will be in the radial direction, okay, as you get further away from the cylinder, okay, in the radial direction. So I'm showing you what that electric field looks like. These are some of the electric field lines, okay, and we're now in a position to evaluate the flux. And as I said, so we need to do this for each part of the surface. Let's start with the sides of the cylinder, and notice here I'm drawing what this vector looks like here, dA. And as you can see, dA, which is always an outward pointing normal, okay, is going to be in the same direction as the field for the sides of the cylinder. If you're on this part of the surface here, dA is again going to be in the same direction as the field. So just like we saw for the case of the sphere, okay, the electric field is constant over that portion of the surface at a given radius, okay, because every little piece of any side here has the same radius. The field should have the same constant value at that same distance due to the symmetry. It means we can take the magnitude of the field outside of the integral, okay, the fact that dA and the electric field are in the same direction gives us a cosine of 0 factor when we do the dot product. And taking it outside of the integral, as we said, will always be the case. Our surface integral, what's left of it is simply, summing up the total area, the infinitesimal area contributions for the sides of the cylinder, which simply gives us a total area of the sides of that cylinder. And when you think about it, okay, think of that cylinder as a cross section as being circular, having a circumference 2 pi r, okay, multiplying it by the dimension L, okay, gives it that extra dimension. So 2 pi r times L, that is the surface area, okay, of the sides of the cylinder, not the ends, but the sides. So there we have that. Notice here, let's turn our attention to the ends of the cylinder, and what we'll find out is that it doesn't matter which end we look at, we're going to get the same result. Let's take a look at the right-hand side here. For this end of the cylinder here, dA, that outward pointing normal, it looks like this. And when you look at it and you look at the direction of the field, okay, you see here that clearly none of the field lines penetrate that surface. That's what the definition of flux is. The flux is zero there. So do you see how this case meets this criteria, criteria 2? The sides of the cylinder meet criteria 1. The electric field was constant in magnitude over the sides. And, okay, for the ends of the cylinder, okay, we meet criteria 2. The electric field being perpendicular to dA, no flux through that portion of the surface. Okay, the flux is therefore zero. So our total flux then is just equal to the flux of the sides. So we're now ready to equate these expressions here. Equate the left-hand side of Gauss's law with the right-hand side. Oh, sorry, we've got to find the charge enclosed by the Gaussian surface first. Okay, my bad. So here, we're given the charge density in this problem. It's given to us, it's lambda. So the charge enclosed is simply the charge density times, okay, the length of that the length of the Gaussian cylinder. Okay, that's how much charge is going to be enclosed by the Gaussian surface. So multiplying the charge density lambda times the length L gives you a measure of the charge enclosed. Now we're ready to equate the left-hand side with right-hand side. And okay, when we do that here, the total flux is given by this, E times 2 pi r L. The charge enclosed, lambda L divided by epsilon naught. We can now solve for the electric field magnitude, and this is the expression we get. So I want to point out here that hopefully it makes sense to you that the the electric field strength, the magnitude, depends on the charge density, right? The greater the charge density, the greater the field strength. Okay, that makes sense. But notice here that we're saying that the field gets weaker with distance, not distance squared, right? There's an inverse relationship, not an inverse square relationship between electric field strength and distance from the center of the distribution. The last example we'll take a look at today is the case of the insulating sheet of charge. So in this problem, we're told that an infinite insulating sheet of charge carries a uniform surface charge density sigma. What is the electric field arising from this sheet? So this, given the fact that the surface charge density sigma, we can assume that this is a two-dimensional charge distribution. If it's an insulator, then so that the charge is spread evenly throughout this sheet, then it must be a very thin sheet to make it two-dimensional. I'm not drawing it that thin, but you're going to have to imagine it's quite thin. And so going through these steps here, identify the symmetry of the charge distribution. Well, it's not spherical, it's not cylindrical. The only other possibility that we said we can apply Gauss's law to is that for a planar charge distribution. And yes, it's a plane of charge. So we're going to choose the Gaussian surface to match the symmetry of the charge distribution such that these two criteria are met. Okay, the electric field is constant in magnitude over each part of the Gaussian surface. Okay, and or the electric field does not penetrate any other part of the surface. Okay, in which case the flux is zero if the field is not constant over that part of the surface. So we are going to choose the Gaussian pillbox, which I said is a right circular cylinder, but it is oriented obviously differently than in the case of the charge distribution, which is cylindrical. So we'll take a look at that in a second when we draw it. Draw the appropriate Gaussian surface so that it passes through the point where the electric field needs to be evaluated. Well, we're asked to find the electric field outside the charge distribution. How about this arbitrary point here, P? This is the way we're going to orient the Gaussian surface. Okay, notice that we place it so that this time the field point is not on a point on the sides of the cylinder. Okay, the field point is at a point on one of the ends of the cylinder. Okay, and that cylinder, okay, we say has a radius r. You know, it could have any length we want. Okay, so we'll show the radius here. Use the symmetry of the charge distribution to determine the direction of the electric field in each part of the surface. So for an infinite sheet of charge, okay, where there's no edges to this, then the symmetry of the charge distribution suggests that the electric field has to be perpendicular to the surface at all points. Okay, it can be perpendicular, but there would not be any components that are parallel to the surface. So the symmetry suggests the electric field would look like this. It's a positive sheet of charge here because charge distribution is positive. If it was negative sigma, it would have to tell you that. So the electric field would look like this. We can now evaluate the electric flux. And you'll notice here that a right circular cylinder has two ends and the sides. So let's start by taking a look at the flux through the ends here. Notice for this end here that the electric field is in the same direction as that area vector dA, in which case the flux is maximized. All of those field lines penetrate the end of that surface. Okay, and the fact that it's parallel tells us that the cosine theta factor is 1, that theta has a value of 0. Also notice that for that distance, okay, every point on that end cap here, okay, every point on this area here of the end is equidistant from the sheet. That suggests that the magnitude of the field should be constant there. Every point is the same distance away. So this is how we use symmetry to kind of facilitate the calculations. And in that case, for this end cap here, at this distance, okay, all points have the same value, the same magnitude of field. That means it can be taken out of the surface integral here. So as always, what's left of our surface integral, we simply sum up all the infinitesimal area elements, which in the language of calculus, that integral simply gives us the total area of this piece of the surface here, which is the area of a circle. We know that the radius of this circle here is r, so we would expect then that the area of it is simply pi r squared. See how easy this is. Okay, the sides of the cylinder here, as we said, you will notice that the field is perpendicular to the area vector dA, which means that there is no flux through the sides. Don't forget the meaning of flux. Okay, flux is a measure of the amount of field that penetrates a surface. Since the field is parallel to the sides, none of those field lines penetrate the sides. Okay, the flux there is 0. So because of that cosine 90 factor, we get no flux through the sides. Now the total flux here, be careful because we have two ends. So we get flux through the right-hand end cap, and we have an equal amount of flux through the other end cap, okay, on the other side of the sheet. So our total flux is really twice this expression here, twice that value. All right, so we can calculate the charge enclosed by the Gaussian surface. Okay, for this really two-dimensional charge distribution, the charge enclosed is just the charge density times the area, okay, of that Gaussian surface, okay, the area enclosing the charge. So here sigma, which is given, okay, is, if I look at a cross section here on this two-dimensional sheet, the area is simply pi r squared. So given this, we are now ready to evaluate left-hand side with right-hand side. And as we said, the left-hand side here of Gauss's law is given by this. The right-hand side is given by this. Don't forget about the epsilon naught there. We've got to divide by epsilon naught. And we see here that, okay, the pi r squared factor exists on both sides. And when you think about it, that should only make sense. Why should a value of the field, why should the strength of the electric field have anything to do with the size of the Gaussian surface that we chose? Okay, there of course there should be no dependence on, the area of an end cap, right? I mean, that would make no sense. So we see that that cancels out, in which case the electric field is this simple expression, sigma over 2 epsilon naught. I want to point out here that for this infinitely charged sheet, notice that this tells you that the field is constant in magnitude, right? It doesn't matter how far away from that sheet you are, okay? The value of the field is going to be the same. Not for a finite charge sheet, but for the infinite charge sheet, that is going to be the case. Right, so now that we have evaluated the electric field for various charge distributions using both Coulomb's law and Gauss's law, okay, today using Gauss's law, I want to summarize some of the results so that we can make a side-by-side comparison, okay, about the field strength here. And I want to go back to the electric dipole, which didn't have sufficient symmetry to figure out the form of the field using Gauss's law. We had to use Coulomb's law to do that. Okay, it was a discrete charge distribution, a collection of two equal and opposite charges separated by a small distance. And I want you to recall that we said that when you're very far away from the dipole, not when you're close, but when you're very far away, that the field dependence went like 1 over r cubed. Okay, that having a charge of one sign and a charge of the opposite sign quite close to it made the field get weaker with distance as r cubed as opposed to r squared. Now the point charge, which we also use Coulomb's law to figure out the electric field for, we know that, according to Coulomb's law, the field gets weaker as the square of separation distance. So, this gives rise to the inverse square law. This is basically just Coulomb's law, which we stated in terms of the point charge. Now, today we applied Gauss's law and we looked at a line of charge, an infinite line of charge. And what we saw was that, as you get further away from this charge distribution, further away from the line, we saw that, the field got weaker as not r squared, but as r to the first power. So this is not an inverse square law. It is simply an inverse relationship, between field strength and distance. And then what we just saw in the last example we looked at for the infinite plane of charge, we saw that basically there was no dependence upon distance, that the field was constant. So long as you are nowhere near the edges of that plane, or you can consider that plane to be infinite in space, infinite dimensionally, then we saw that the electric field was constant, that as you went further away, it did not get weaker, that the field had the same value. So long as, like I say, this was an infinite sheet of charge, a plane of charge, so it either has to be infinite or you have to be close enough to it that you're very far from the edges. And lastly, we'll take a look at a rather simple problem where we can use what we talked about in the previous slide to make some approximations that can really simplify the problem. So here we're asked to estimate the electric field for a uniformly charged disk. Now, Gauss's law would not apply exactly to this problem, if the disk is finite in dimensions. This is not a symmetry that is sufficiently high when we don't consider it to be infinite. And the Coulomb's law calculation would prove very difficult for the field. But here's what I want to show you. We can make an estimate, that can be done rather quickly. And remember what we talked about in the previous slide. If we're looking at points that are very, very close to this disk, that are not close to the edge of the disk, then we can consider it to be essentially an infinite plane. In which case, we know that, okay, the electric field for points very close would be directed perpendicular to the plane of the disk itself. Okay, this is really like the last problem we did applying Gauss's law. Likewise, if we were very far away from this disk, okay, this disk is going to look like a point charge to us. In which case, we know that for a point charge, the electric field has this radial symmetry. And remember, you get far enough away from any object and it's going to look like a point charge to you. So what I'm saying is that if we're looking at points far away, we can think of this as a point charge having radial symmetry. Now, it turns out that for points in between, the shape of the field is much more complicated. Okay, but we know that the electric field is a continuous entity, and therefore it must connect, okay, continuously. It must smoothly connect. So without actually doing any sophisticated calculations, we can say that in order for this field to be continuous, we can connect these two regions, okay, and we can approximate the field, okay, to look something like this. So there we have it. This is a way to, use some approximations, to perhaps solve a very difficult, if not impossible, problem to solve using Gauss's law or Coulomb's law.